Okay, 26. And so what does this come out to be? What? 0.050. And now we need to plug that in. So we have d equals the square root of 0.050 times 12.14. And what does that come out to be? Point 2.71, and the actual was 2.5. Not bad. So using methods very similar to this, Rutherford was able to figure out what the diameter of the nucleus was. And this was a really important achievement of the time. Okay. So in the last few minutes, maybe I'll move this down. In the last few minutes, we want to talk about the fallout of all of these great experiments and all of these great results. So we now know there's an electron in a nucleus. So they're subatomic particles. What does that mean in terms of what people thought they understood about atomic theory? So we had this question then. OK, so we have a nucleus, positively charged, and an electron, negatively charged, and there's a distance between them. They wanted to know, why do they stay apart? Why does the electron not crash into the nucleus? So from classical description, we have Coulomb's force law, which tells us about the force when you have two charged particles, Q1 and Q2, so the charge on the particles. And you have over 4 times pi times this E0, this permittivity constant, times the distance, r squared. So if you apply a force then, and you have charged particles, if those particles have the same sign, then acceleration should push them apart. The force should be positive and repulsive. So two things with the same charge don't want to be near each other. It's going to be repulsive. If, like in this case, you have two things that have opposite signs, acceleration should pull them together. And here, the force should be negative and attractive. So that's the situation we're in here, positively charged nucleus, negatively charged electron. So let's consider then a hydrogen atom. Z equals 1 electron, 1 proton. Let's think about what happens when you have an infinite distance between them. So if they're infinitely far apart, what is going to be the force? You can just yell out the answer. 0, right. They don't feel each other. They don't know anything about each other. They're infinitely far apart. There's no force. But that's not going to be the situation in the atom. Atoms are small, so they're going to be somewhat near each other. Now we can think about what happens if they're right on top of each other and r is 0. And here we can try out the clickers one more time. OK, so we'll do 10 seconds. Oh, the color's changed. So most people it's infinitely attractive. So infinitely attractive, like most chemists. Except Avogadro. He's very strange looking. OK, so if these things are going to be close to each other, then they should be attracted to each other and collapse into each other. So why then are the electron and the nucleus that are infinitely attracted to each other, why do they stay apart? So Coulomb's law is not helping us understand this, but it's really just talking about the force with respect to a distance. It's not telling us anything about what happens when r changes with time. So we'll find in chemistry sometimes that things are spontaneous in one direction, but they're also very slow. So you don't have, the thing doesn't happen, it's just kinetically very slow. So let's consider time now, and maybe that will help us understand why this is not working. It doesn't, but let's look at that. So what do we know about time? What do we know about acceleration and force and time? We need a classical equation of motion that can explain how the electron and the nucleus could move under force. So we have our good friend. We have Newton's second law. We have F equals ma, force equals mass times acceleration. So let's think about what this tells us about the electron and the nucleus. So we can express force as a function of velocity. We can also do that in terms of distance. So now let's think about what's happening. We know the force. We can calculate the force from the Coulomb's force law, the force between the nucleus and the electron. And then we can think about two different distances, and with that force, how fast the particles should move toward each other. So for the initial distance, we can take 0.5 angstroms, or 0.5 times 10 to the 10 meters. So that's about the radius of a hydrogen atom. So we take that distance. And then we want to think about how fast that would then go to 0. And it's fast. Approximately 10 to the 10 seconds, or the electron should plummet into the nucleus in about 0.1 nanoseconds. It doesn't do that, though. So we have these beautiful classical laws. I'm a big fan of F equals ma. I like all these things, but it's not working to describe what's happening here. So we discovered the electron, discovered the nucleus, but now we have a new problem. We don't understand why the electron isn't plummeting into the nucleus. So what's the problem here? So is the problem Coulomb's force or Newton's second law? And it turns out, as most of you are probably aware, it's that classical mechanics doesn't work when you consider things on this size scale. So we need a new way to describe what's going on here. Classical mechanics isn't working, and so we need quantum mechanics. And so that is allowing us to understand the behavior that we're actually observing. We're not observing this plummeting, so there must be a better way to do this. And when you're on this really small scale, you need a different way to describe the behavior. And so next week, we're going to be moving in and thinking about quantum mechanics. And if anyone's still having clicker questions or needs a clicker, we'll be down here to help you out. And otherwise, I will see you on Monday.